Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management of JRS Group. Today I am going to take a class of Signal and System. This is the lecture number 3 and today's topic will be classification of signals and the different significance and characteristics of signals. So let's start. This is the lecture number 3, Signal and System. Today's topic, the things that I'm going to describe or discussed about. Today's discussion points are signal energy or energy signal, signal power or power signal, and different kind of elementary functions. So let's start with signal energy. Signal energy and power. We see that signals may represent a broad variety of phenomena. Many signals we consider directly related to physical quantities capturing power and energy in physical system, such as energy of current. We used to have different kind of LC circuits. In LC circuits, the LC circuit used to capture a sinusoidal exponential signals. This is the factor. A signal that has been captured usually is a total sum and effect of different physical phenomena, different physical quantity are encaptured in a signal. So, such an example of voltage, as I've told about current signal, as it varies with time, and respectively the voltage and current across a resistor with the resistance R, the instantaneous power. In case of this, if I talking about RC circuit or suppose an RLC circuit, in case of RLC circuit, a closed loop on RLC circuit where there is a voltage and current which is going going across through the resistor. The resistance amount to R. Then the instantaneous power is, as we have known from our earlier studies, that the power, then the instantaneous power in the resistance R will be P function of t is equal to P function of t into I function of t, which can be expressed as 1 by R into v squared to t. So we are going to use similar terminology for power and energy for any continuous time signal x function of t or any discrete time signal. It means basically any kind of continuous time signal or a discrete time signal is nothing but the expression, as an encapturing expression of different kind of physical phenomena. All those physical phenomena are being captured in a signal. A signal is basically an expression of all those physical phenomena. The sum of a physical phenomena is an expression it expresses as a signal, nothing but else. So that's why, as we can use all this voltage and current and different phenomena to calculate the power across a resistance R, that could be V into I or 1 by V square R. So here we can also use all those significant analysis to analyze the signal power and signal energy. That's why you use all this terminology. Those are similar to calculating the power energy of a resistance R. All these equations will be used to calculate the energy and the power of a signal. Now we can define the total energy and average power over a time interval in the same way for different signals, such as that has been explained in the next slide. Please. Signal energy. The total energy over a specified time interval in a continuous time signal is integration of x function of t whole square to dt. It means that function that describes the signal. If I take a square of that and make an integration of that, specific expression, we will get the energy of that signal, nothing else. Where we could take any specified time interval. Now that integration, we can, as we have known earlier, that if I have to count or calculate the signal energy of a specified time interval, suppose there is a signal that has been started from point 0 and it ends at 5 or 6, or it could have been not end at 5 or 6, but we want to calculate the signal energy between the 0 to 6. In between that point, the amount of signal energy has been calculated. Or if we want to calculate that signal energy, what we'll do, we'll integrate the specific function, we'll integrate the specific function square from, in that case the lower limit of integration will be 0 and the upper limit of the integration will be 6. That's the specific expression to calculate the energy of a signal. Now there has been described here where the mod x denotes the magnitude of the possibly complex number x. Similarly, the total energy in a discrete time signal x function of n over a specified time interval would be in the same case f suffix n x suffix of x function of n whole square. We will take that expression of x function of n whole square and we will take a summation of that specific expression of discrete time signal. Now where we could take any specified time interval in case of when we were summating that whole expression, in that case also we have to, if we have to take a lower limit and upper limit of integer value, we will take that and we will calculate that signal energy, discrete time signal energy around that specific integer value. If we have to calculate the signal energy, discrete time signal energy between 0 to 6, we will use that expression, and the upper limit will be 6 and the lower limit will be 0. Same in both of the expressions for continuous time signal and discrete time signal. Both the expressions are same, but in case of continuous time signal we use independent variable t in a continuous manner, and we use x function of n, where n is the integer value, different integer value. Okay, now next, where as we have earlier said, the PPT is also saying that where mod x denotes the magnitude of the possible complex number x. Now let's go to the next slide. Now if I have to calculate this power of a signal, how will I do that? Some signals have infinite signal energy. It depends. Some signals have infinite signal energy. In that case, it is more convenient to deal with average signal power. That's a very important factor. For power signals, the upper limit and the lower limit could be from 0 to infinity. Okay, so in case of when you are calculating a power of a signal, in case what you have described in earlier statement, that power could be in between 0 to infinity, and the energy of power signal will be infinity if you have to calculate that way. So the equation that we use to calculate the power of a signal is Px is equal to limit t tends to x 1 by 2t, and the time integration will be minus t to t. It basically means that in the earlier, if we get back to the earlier slide, let's get back, that signal energy, when we calculate signal energy, we use this expression. Simply we use this expression. Now if I have to calculate the power, what I will do, I will just average that signal energy. I will divide the whole expression by the total time limit, through which time limit or the expression limit through which we integrate the whole expression to get the signal energy. If I have to evaluate, or if I have to conclude the power energy, if I have to extract the power energy, what I have to do, I will just divide the whole time limit. If we take a closer look here, that the time limit here is from minus t to t, so the total time limit is 2t, the total time through which we have calculated the energy of that signal. Now if the total energy of the signal, is divided by the total length of the limit, then we will get the power of the signal. This is as simple as that. If I just, this is the lower limit, this is the upper limit, we integrate that and we get the energy signal. Now if we just divide the total energy of the signal by the total length of limit, then we can extract the power signal. This is the expression for continuous time signal, and this is the example, the expression for discrete time signal. In case of discrete time signal, we use the same process, x function of n whole square. We summate the x function of n whole square, and the lower limit is minus n and the upper limit is plus n, and we'll divide the total energy of the discrete time signal by the total length of the limit. And in this case, as you can see, 2n plus 1 will be the total, as because from minus n it will go back to 1, that is minus n. 1 is for 0, the value of the signal, discrete time signal value will be, there will be some value at 0 point, at n is equal to 0, the discrete time signal will have some value, so that will be also calculated, and then from 1 to n the whole number will be calculated in that way. So as we can see that if I have to calculate the power of any signal, we just have to divide the length, we have to divide the signal of the energy by the length of the limit. Through that we can extract the signal, power signal, or the power of that signal. Okay, let's go to the next slide. Okay, this is the power signal, this is the energy signal that we have. I have already explained all these things, that a signal with finite energy. Now a signal with, this is an important factor, all this conclusion has been extracted from the equations. This is the very similar equation that I have been already earlier, I have already explained all these things, that we will take the whole square, we will take the integration of the through the length of the limit, and we will get the energy signal. And if we divide the length of the limit by, if we divide the energy signal by the length of the limit, we will get the power signal, or the power of that signal. Now a signal with finite energy and zero power is called energy signal. Why I am going to explain that. A signal with finite energy, suppose a signal has a finite energy and zero power is called, why it is zero power? It means that the whole integration, it means that a signal is divided by the length of the limit. Now the total energy of that signal is finite, is very finite, and that's why it is called, now if that signal doesn't have any power, then it's called energy signal. And for energy signal, this statement has a mathematical interpretation, is that energy signal, the energy should be between 0 and infinity, and the power will be 0. And in case of energy, this is for signal, this is called energy signal. Now in case of power signal, we will have a inverse characteristics or inverse property. Say that the units are, now the units of signal energy depends on unit of the signal. Simple. The energy of the any kind of the energy, the unit of that energy will be the same that we have already known from the past. Now let's go to the next slide. Now this is, now as we have explained that that's a signal with finite energy and zero power is called energy signal. In case of power signal, the whole thing will be inverse. It means that in case of power signal, the power will be finite and the energy will be different. Yes. Now example, this is a different example of how we will calculate the power signal. So in case of the example is the periodic signals, and in particular the complex periodic exponential signal and the sinusoidal signal in provided with infinite total energy but finite average power. Infinite total energy but a finite average power. For example, consider the periodic exponential signal. Suppose that we calculate the total energy and average power in the complex exponential signal over one period. That any different kind of exponential signals and different kind of sinusoidal signals that we have discussed earlier. Now we are going to calculate the energy and the power of all those specific signals, and we'll conclude that a sinusoidal signal, the discrete time or continuous time complex exponential signal, will have an infinite total energy but finite average power. Let's check it out. Now the power and energy calculation of periodic signal. What we will do, we will have a exponential function. The expression of an exponential function or exponential signal will be what? E to the power j omega 02. Now that is the function. So what we will do, we will square that function and we will integrate that function through a specific length of limit. Now here we have taken from -1 to 1. Now we'll integrate that function. What we will get? We will get 1. It means the power is finite. This is the point. The power is finite because if we integrate a e to the power function, we will derive this 1 from that specific integration of e to the power j omega 02 whole square. We will get 1. So any kind of exponential function, if we integrate through a length of limit, using a length of limit, we integrate an exponential function, we will get 1. Now if we consider the energy of that signal, energy of signal of exponential energy of exponential signal, what we will get? We will get this e to the power j omega 0 to dt 0 to t0, and we get the t0, the fundamental time, the t0 is the fundamental time. We will get this from this specific function. Now if we go back to the previous slide, we have to have already said the periodic signals, in particular the complex periodic exponential signal and the sinusoidal are is provided with infinite total energy but finite average power. There is the average power is finite, but the energy of that signal is the energy of the energy signal is infinite. That's the process. Now let's get that. Okay, so this is the end of the power energy signal. In case of there's a very important factor is that in case of complex exponential signal, the energy is infinite but the power is finite. That's the most important factor. In case, because as we have known, the exponential signal is basically a sinusoidal signal. The sinusoidal signal has very finite power but infinite energy. Let's go now. This is the end of the signals. Now we'll get the topic we want to discuss is elementary function, different kind of elementary function. Today I am going to explain unit function, impulse function, and ramp function. Okay, so let's start. Okay. Now it's unit step function. The unit step function is basically a expression of a function. We can also explain a signal using this function. How will now we're going to describe that. Unit step function is nothing but this is the expression of a unit step function. Now, if unit step function is equal to 1, when it is going to be 1? It's going to be 1 when t is greater than 0. Now, this equation is showing that when t is any time when t is greater than 0, the value of that function will be 1. This is the expression of that signal. Now, or this can also be a unit step function. When the same thing will happen, that it is ut is equal to half if t is equal to 0, and ut is equal to 0 if t less than 0. It means if the value of t is less than 0, the value of t is less than 0, then the function u function of t is also 0. And now if u function of t is equal to 1, is going to be 1 when t is greater than 0. That is a unit step function. It means the what is the step? The word step describes itself that a function is 0 at very point. Now the next very point it could be 1. Now it is going to be 1. That's why it's a step. It's a step function. It's just like a staircase. The staircase is at a very granular level. It's very a 0 level, ground level. And at the very next step, it takes a jump. That's why it's called a step. That's it's a step function. Any kind of step function is not going to increase gradually. It will increase. It is a stepwise increase will be occur. That's the characteristics of a unit step function. Now let's go back to the next function that I'm going to describe is different kind of unit step and unit impulse function. Now first I'm going to describe the unit impulse function. Okay, what is the unit impulse function? So very much similar to that. It's a very minor difference there. In case of unit impulse function, it's if you first understand the expression. The expression is if this is the expression of unit impulse function. Now if it is going to be 0 when the n is not equal to 0. Now if n equal to 0, then the function will be 1. Very similar. Now if we get back to the previous slide, what will we get? We'll get this. Now this is a very simple discrete time unit step function where up to 0 the value is 0. Now after 1 is an abstract jump of the signal. It's all at one value. Okay, but after t greater than 0. Now in case of if you take a closer look on this function, what is this? This is a unit impulse function. How it will work? It's work as it's a 0 everywhere. Okay, but at n equal to 0, it's this. Now it could be 0 again, and after some time it could be also there's a jump, and suppose at n equal to 0 this value is 1. Now after 15 steps, after 15 suppose at n equal to 16 this value is also again repeated. It means at n equal to 0 is at n equal to 0 the del function of m or n is equal to 1, but at also it could be also 1 at n equal to 16. That is also, this is a unit impulse function. So okay, now let's get back to the next slide. Step impulse. Now so important characteristic of unit impulse function is the derivative of unit step function, or unit step is the integral of the unit impulse function. It means if we take a derivative of unit step function, we will get a unit impulse function. It means if we add stream of unit impulse function, we get a unit step function. It's as simple as that. Unit step function is a summation of many unit impulse function. That's why if we take a derivative of unit step function, we get a unit impulse function. Now if we take 100 of unit impulse function and we integrate them, we get a continuous unit step function. It's as simple as that. It all started at 0. Unit impulse and unit step both started at 0, but in case of unit step the function will continue from 0 to somewhere else up to what the function limits are described or prescribed. But in case of unit impulse function, the unit impulse function, there is a difference, and the difference is, as we know that for unit step function, the function will continue from 0 up to some point, or could be for infinity. But in case of unit impulse function, that continuity will not be maintained. It could be sometime it is a 1, for few integer values there will be 0, but after that it could be again comes with a value. That's why unit impulse function is a derivative of unit step function, or unit step is the integral of the unit impulse function. Okay. Let's go to the next step. Next slide. And this is the unit ramp function. What is unit ramp function really describe? It's simple, it's also simple as that RT is equal to t when t greater than equal to 0. When t greater than equal to 0, the value of function is t. Other than that, when t is less than 0, look, the value is 0. But when t is greater than 0, the value of RT is this. It's as simple as that. How it is work? It works as this. RT is equal to t into ut. Unit step function into t. It means RT will be described, it will be exist when t is greater than equal to 0, but it's not a unit step function. Why it is not a unit step function? Because it's a unit step function with a specific amount of value. That's why this function has been described in this way. Now if we take a derivative of ut, if we take a derivative of this, we will get 1. As you can know that if we take a derivative of this, we will get this. And if we can also explain that our function of n is described the same way. This is for continuous time signal and this is for discrete time signal. This function is described in both ways. Thank you very much. Okay. For today this is for all. And from the next slide we are going to describe many other elementary signals. Thank you.